Hi, Assalamualaikum. My name is Rashadah binti Abdul Rasid. Today we will discuss about first law of thermodynamics. Okay, thermodynamics, very universal life of study. So before we start, let's introduce some definition. Okay, in study thermodynamics, we want to divide the universal into two parts, which is system and surrounding. So, the system is part of the universe on the study, and the rest of the system in the universe is called surrounding. We can divide our system with the surrounding using a wall. So, the wall is pretty much a barrier, and the type of wall that we use define the system boundary condition. So, let's look at the different type of system that we can have. So, when we have the wall that both is permeable and dithermal, we will have an open system. So, an open system is characterized by the exchange the matter and the energy. For example, living organism which breathe in and breathe out the air, for example, to exchange heat with the surrounding. Other type of system include a closed system. So, if a wall become impermeable, we have no longer exchange of matter with surrounding, but we could still exchange energy. So, most of the symbol system will be talking about thermodynamic discussion. So, another type of system is an isolated system. Now, a wall is going to be impermeable and adiabatic. So, there is no exchange both matter and energy. So let's now look at different type of properties of the system. So overall properties that's macroscopically observable that define the state of system. So we have two major type of properties. So we have extensive and intensive properties. Extensive properties that's going to be dependent on the amount of matter present. The sum of the properties of part 1, part 2 and part 3 is equal to the wall. So the example of properties include volume, internal energy, enthalpy, entropy, and number of moles. So we have also another type of properties, which is the intensive properties. So the intensive property is going to be independent of the amount of matter present. If we have intensive properties, so if we measure the intensive property over the part 1, 2, 3, and 4, they're going to the same as property of the wall. So this is going to be constructive intensive properties that are additive. The example of intensive properties are temperature, pressure, density, and molar quantities. Of course, when we start talking about thermodynamics, we have also the another things that we need to define before we are going to anything else. That is, what is energy? We use an energy a lot in everyday in life, but what is it exactly? Okay, from textbook define energy is the ability to do work. Of course, when you analyze the definition, what is that mean with do work? So when we go to definition, work, however, what is defined as a method of energy transfer. So the definition is kind of circular become if we look at this, it pretty much defining energy is the ability to transfer energy. Let's look a little bit more closer to the in term about system and surrounding. So a system is going to have internal energy. So internal energy is symbolized with capital U. So the internal energy is the total energy that's in the system. Changes can happen if we have the transfer of this energy to the surrounding. So we could transfer energy through work for once, but work can also transfer energy by heat. So let's just add additional classification on heat. So heat also is defined as a method of energy transfer. So there are two methods to transfer the energy. So when we transfer this energy, we are going to be changing the internal energy in the system. So the changing of the internal energy can also associate with changing in other properties of the system. Okay, of course we are transfer this energy. It have to go somewhere we put in surrounding, right? The surrounding also have its own internal energy. Since it also has internal energy, the process could also go in reverse way. That means the surrounding could also transfer energy as well or heat into the system. So let's look closely what is exactly means by internal energy. So we set a total energy of the system. So how do we look at this exactly? So we could divide the internal energy into two major parts. So we could define the internal energy as total sum of kinetic energy and the total sum of potential energy. So we talk about kinetic energy, which is energy of motion. Okay, so this is the equation of the kinetic energy. The another part is potential energy. So let's also look at potential energy here. There are a lot of different type of potential energy. So potential energy is just our stored energy. So we could have chemical potential energy, electrical potential energy, nuclear potential energy, gravitational potential energy, and many more. So this is the part of property made in determining the internal energy of the system. So there are different type of potential energy in all these things. Very hard to measure, so alternately it's really hard to measure potential energy. It's also very hard to measure internal energy, so it's never really possible to get absolute value of the total internal energy of a system. But luckily we are not interested in determining the exact internal energy of the system, okay? But we usually interested after all are changes, right? Our interested in how internal energy change after undergoes a process, namely if undergoes a transfer of this energy as well or heat. So interested in the changes of internal energy, the delta U is equal to the internal energy of the final state minus internal energy of the initial state. So again, we are not interested in absolute value of internal energy, but rather than changes. So something goes to surrounding actually. So we could also have a change in internal energy in surrounding of this process over here. So we also have a corresponding delta U for surrounding. So if we have a system and it transfers some of the internal energy to its surrounding, it has to be relationship between them. The way the delta U of system changes and delta U of surrounding changes. If ever were decreasing of the internal energy of a system, okay, this has to lead to the corresponding increase in the internal energy of the system. So the change of internal energy of system is going to be in equal manner to but opposite sign to that of surrounding. Okay, this principle is overall just be first law of thermodynamics. So, the first law of thermodynamics tells us that the energy cannot be created nor destroyed. It only could be transformed or transferred. So, when we say in transform, that means an energy could take a different type of form. It could be in terms of kinetic energy or can be in terms of potential energy. So energy transfer could be to the heat or work. Okay, so let's look at different way you get measure changes in internal energy. Okay, keep in mind of the first law of thermodynamics, there's two major way which we could change internal energy of the system. Which is transfer energy via work or via heat. Okay, so what we are consider change in energy? Let's consider in terms of small changes. So we could represent small changes by differential. So look at differential of internal energy, which is du equal to dw plus dq. dq is going to be the sum of small work being done, and dq is internal small heat that being transferred. So internal energy is the type of differential is called the exact differential, and the differential for work and heat in thermodynamics we call inexact differential. So we could see the significance of this difference when start to integrate this differential. So look into integrating, going to be integrating from initial to the final state in order to get the overall change in the process. So this over here, we get the express as delta U is equal to W plus Q. So the change in the internal energy is just equal to the work that has done as well as heat that was transferred. So why do we have to make the differentiation between exact differential and inexact differential? This has something to do with state function. So we get expressed differential as exact differential is dealing with called state function. State function are usually expressed capital letter. So this means that there are path independent. So meaning that if we evaluate in differential will depends only on final and initial state. So for non-state function like heat and work is path dependent. The quantities are going to depend on path that we taken in order to get from initial state to be final state. Because of this law, we can outline a few different type of processes that can occur. If a process occurs where there is no change in the volume of the system, that means that no pressure volume work can be done or by the system. So work is zero in such a case. Delta U equal to Q, and any change in internal energy must be the result of heat transfer in or out. This will be called an isovolumetric process with no change in volume. An example would be a bomb calorimeter where a combustion reaction produces a change in temperature but the rigid wall results in no change in the volume. If there is no change in temperature of the system, there cannot be any change in the internal energy of the system. Since these two values are proportional, delta U will be 0, which make Q equal to negative W. This means that any heat transfer into the system is used by the system to do work rather than increasing the internal energy of the system. This is called an isothermal process, meaning no change in temperature, and either version of a car engine could be an example of this as the piston ought to convert all of the heat energy from the combustion reaction directly into expansion work that move the car. If there is no heat transfer, Q will be 0 and delta U will equal to W. This means that the internal energy of a system change are a result of doing work on its surrounding. Or the surrounding doing work upon the system. Such a process will be called an adiabatic process, meaning no heat transfer. We can see this certain process in Earth's atmosphere as masses of air change position due to pressure difference. And if Q and W are both 0, meaning there is no transfer and no work done. There can be no change in internal energy, and this must be an isolated system. For example, a thermos flask is used to keep things either cool or hot. Hopefully, these scenarios make some intuition sense because we will frequently use this equation to do calculation. We will also need to define the sign of these quantities in order to use this equation properly. So, let's take note that when heat is absorbed by the system, Q will be positive. If heat is lost by the system, Q will be negative. W is negative when work is done by the system. The system has to expend energy to do work, and so the internal energy of the system decreases. W is positive when work is done on the system. Let's look into the example of first law of thermodynamics. Okay, look at the first example, which is the boy who is running. His chemical energy is allowing his muscle to move, and that's turning in his kinetic energy for his entire body is moving. But at some point, some point he stopped. Where did all the energy go? Well, some of it will be heat in his body that's being dissipated into the border system, into the air. And also when he was running, there was discontent of the ground vibrate a little bit. Some of it will be transferred as sound. So the air particle moving through the air, and a lot of it will be heated, and we are going to see this over and over again. Okay, the second example is when we hit a pool ball right over here, some of the energy might be going to hit the next ball, but at same point they are going to stop. So what happened to that energy? While the pool ball are rolling, there was some air resistance, so they are bumping against these air molecules, and it is really friction due to air and energy converted to heat. A system progress a lot more of the energy tend to turn into heat rather than doing useful work, and we are going to have as the pool ball move. There is the ball that will be partially transformed from kinetic energy into thermal energy. There is also friction that occur on the table, which causes the molecule to rubbing with each other and will cause it to turn hot. Since kinetic energy is moved from friction, we will no longer have kinetic energy. Okay, the third example is weightlifter. He uses the chemical energy at ATP in his muscle, which move this weight. But once he is in this position, what happened to all that energy? Much of the energy is now stored in potential energy. The object will fall off quickly and has been stored in potential energy, but he will also produce heat. Even the act of moving it through the air will be hot in the air. Some friction will with it. I want you to appreciate that this energy does not come out now here. It is converted from one form to another, or it is changed from one form to another, or transferred from one part of the system to another. Okay, let's look how do we calculate the first law of thermodynamics using the formula, which is delta U equal to Q plus W. Okay, for the example 1, which is 100 joule of work is done on the system. So we know that work is done on the system, so work is positive. Okay, internal energy increased by 74 joule. How much energy is transferred as heat? So we use the equation, and then we include the value of the equation given, and we got the answer, which is Q equal to negative 26 joules. Okay, let's look into the example 2, which is a gas start with 200 joule of internal energy. While you add 180 joule of heat to the gas does 70 joule of work. Gas does 70 joule of work. That's meaning that work is done by the system, so you will have the negative W. And then what is the final internal energy of the gas? Okay, and then you put the value what you get in the question into the equation, and you will get the answer. Okay, this is the last example, which is the example 3. Okay, a certain gas stands from 250 ml to 720 ml very, very slowly at 25 Celsius. If there is 1 mole of gas in the chamber, calculate the work involved when the gas behave ideally. So the formula we use is work reversible is equal to negative nRT ln bracket V final divide by V initial, and then you include the value and you will get the answer. Okay, that's all from me, Rashada binti Abdul Razid. Thank you so much for watching.